This video is on using different proof techniques. So far we've seen three techniques. We've seen direct proof, including using cases. We've seen contrapositive proof. That's where to show P implies Q, we instead show that the negation of Q implies the negation of P. And we've seen proof by contradiction, and that is where we assume that the original statement is false and then eventually come to a contradiction. So I wanted to do a few examples where we're just asked to prove a statement and then consider what proofs would look like of these statements using different techniques, or see situations where one technique is a lot easier than another, or vice versa. So let's look at proving the statement, if x squared plus 4x plus 6 is odd, then x is odd. So I'd like you to think about which techniques could be used, as well as thinking about how the proofs would go in each case. So give that a try, and we'll talk about it in a moment. Okay, let's just think about what techniques could be used and what a quick sketch of each of them would look like. So could we use a direct proof in this case? So could we use direct? Well, if we did a direct proof, then we would be starting with the hypothesis. So suppose that x squared plus 4x plus 6 is odd. What would that mean? Then x squared plus 4x plus 6 is equal to 2k plus 1 for some integer k. And then we would be trying to show something about x. So we would at that point want to show that x is odd. We want to show that that x is equal to 2j plus 1 for some integer j. Well, that's kind of difficult to prove just given this assumption. We'd want to get x by itself, presumably, and how could we even do that? We'd be getting into things that would not necessarily even be integers. We'd be doing a lot of divisions, and so in this case, a direct proof is not the easiest way to go for sure. How about a contrapositive proof? So contrapositive. We know that if we are doing a contrapositive proof, we want to show that not Q implies not P. So in other words, we would suppose the negation of our original conclusion. We'd suppose that x is not odd. If x is not odd, then x is even. And so x is equal to 2k for some integer k. And if that's the case, then we could consider the original expression, x squared plus 4x plus 6, that's equal to 2k squared plus 4 times 2k plus 6. And what do we want to show? We want to show the negation of p. We want to show that this expression would end up not being odd but even. And I think it's pretty clear that that is going to be an even integer. So like I said, I just wanted to do a sketch for now, as opposed to doing the whole proof. But yeah, we would show that's even, and it looks like this would work out pretty well. So contrapositive proof in this case would work out pretty well. What about if we tried to do a proof by contradiction? So if we did contradiction in this case, then we would be trying to first assume the negation of the original statement. So we would assume the negation of the original statement, the negation of a statement we're trying to prove P implies Q. We know that the negation of a statement of the form P implies Q is P and not Q. So P and not Q is the negation of P implies Q. And so we would be assuming that, suppose for contradiction, that the first piece is true, that x squared plus 4x plus 6 is odd, and the second piece is false, x is even. And we would be trying to arrive at some kind of contradiction. What kind of contradiction could we arrive at? Well, we could do the same thing that we did in the contrapositive proof. We could say, since x is even, x is equal to 2k plus 1, is equal to 2k for some integer k. And what would that mean? That means that then x squared plus 4x plus 6 is equal to 2k squared plus 4 times 2k plus 6. And we could do exactly what we were doing up here. We could just factor a 2 out of this after simplifying it and show that this is even. And so we would then arrive at a contradiction, and our contradiction would be, okay, x squared plus 4x plus 6 is odd, and x squared plus 4x plus 6 is even. And so we would have shown that this is both even and odd, which of course is impossible, and that would give us a contradiction. So that's what proof by contradiction would look like, and yeah, that works out just fine as well. One thing I wanted to note in this case is that these two proofs are very similar. So when you're proving P implies Q, proof by contradiction and proof by contrapositive are actually almost exactly the same in their structure. So if proving a statement of the form P implies Q, then proof by contrapositive and proof by contradiction are very similar. In this case, for the contrapositive proof, assuming the negation of what you originally wanted to show, you are assuming not Q. In contradiction, you are also assuming not Q. And then with contrapositive, you're trying to eventually show not P. With contradiction, you are also trying to eventually show not P as well. So showing this was even is showing not P. And then you're showing that, okay, that is a contradiction with the assumption that P was true. So you're really showing not P and P. You assumed that P was true, but you showed that P was false, and that is what gave you the contradiction. So contrapositive proof and proof by contradiction are very similar if you're proving a statement of the form P implies Q. Okay, so we've only really done a sketch of this proof. Let's go ahead and finish it off using one of those techniques. I think that proof by contrapositive is the easiest to do here. So this is a proof by contrapositive. Suppose that x is even, or suppose that x is not odd, then x is even and x is equal to 2k for some integer k. Therefore, x squared plus 4x plus 6 is equal to 2k squared plus 4 times 2k plus 6, and we want to show that that is even. This is equal to 4k squared plus 8k plus 6, which we can factor a 2 out of. That's 2 times 2k squared plus 4k plus 3. So we've factored a 2 out of that. And we can say which is even since 2k squared plus 4k plus 3 is an element of the integers. So we have now proven if Q is the negation of Q implies the negation of P, and so we have done this proof by contrapositive. Okay, let's look at proving another proposition. Let's try to prove that the set 0, 1 has no smallest element. So again, think about which technique can you use and start to think about a sketch for whatever technique you try. So which technique could be used and what would the sketch look like in each case? Okay, let's think about what techniques could be used to prove that the set 0, 1 has no smallest element. Okay, so our first technique is direct proof, and in this case, I would say there's really nowhere to go. The set 0, 1 has no smallest element. There is no if to suppose. If there are no assumptions to be made up front. There's nothing to start with. So how to even start with a direct proof, I think, is quite challenging. So I would say, no, that's not the best technique to use here. What about contrapositive? So we know that to do a contrapositive proof, to prove something of the form, so to show P implies Q, we instead show not Q implies not P. But this statement is not of this form at all. So this is not of the form P implies Q. This is not a P implies Q kind of statement. And so we can't use contrapositive at all. So it is just not possible to use contrapositive proof on this statement. What are we left with? This must now be a proof by contradiction. So let's go ahead and start it. Proof. Well, if we are contradicting the statement that the set 0, 1 has no smallest element, well, if it does not have no smallest element, then it must have some smallest element. So suppose for contradiction that the set 0, 1 does have a smallest element. And so it does have some smallest element. It's often useful if you're doing a proof by contradiction like this to go ahead and name that element so that you can start doing things with it. So suppose that the set 0, 1 does have a smallest element, and we could call it the element x. So x is now the smallest element in 0, 1. We could do some scratch paper over on the side and say, okay, so x is in the set 0, 1. That means that 0 is strictly less than x, which is strictly less than 1 because it's open parentheses. I want to contradict my original statement. I want to contradict this statement. I want to contradict that x is the smallest element. So I want to show that x is not the smallest element in 0, 1. So how could I contradict that? I could contradict it by find something smaller. So I could contradict that by finding something smaller. So if x is in the set 0, 1, if x is between 0 and 1, is there something that I know is definitely smaller than x that is also in that interval? So think about that for a moment. Could there be something smaller than x that's in that interval? Well, if I subtract from x, I don't necessarily know that if I subtract that it's still going to be greater than 0. But what if I divide x? What if I consider x divided by 2? Well, I know that x divided by 2 is less than x because x was greater than 0. And x over 2 is also going to be greater than 0 because, again, x was greater than 0. And x over 2 is also going to be less than 1. So I do have something smaller now. X over 2 is smaller than x, but it is still in the interval from 0 to 1. And so now I have my contradiction. So I've supposed that x was the smallest element. Let's consider x over 2, which is less than x because x was positive. And observe that since x over 2 is less than x, which is less than 1, and x over 2 is greater than 0, since x was greater than 0, this tells me that x over 2 is in the interval from 0 to 1, and x over 2 is less than x. So this contradicts our original statement. So this contradicts that x is the smallest element of the interval from 0 to 1, and therefore the interval from 0 to 1 has no smallest element. Okay, let's do another proof and think about what technique would be most useful with this. So let's prove that if x is congruent to 1 mod 3, then x squared is congruent to 1 mod 3. All right, let's think about different potential techniques for proving this statement. Let's first think about what would it mean to do this by contrapositive proof. So if we were doing this by contrapositive proof, then again we would do not q implies not p. That's what we would be trying to show. So we would be saying, okay, suppose that the negation of q, suppose that x squared is not congruent to 1 mod 3. What would that mean? That would mean that then 3 does not divide x squared minus 1. That would be one definition we could use. So 3 does not divide the quantity x squared minus 1, and we would be trying to show that 3 does not divide x minus 1. So we would say we want to show 3 does not divide x minus 1. So 3 does not divide x squared minus 1 implies that x squared minus 1 is not equal to 3k for any integer k. And that's what we would be assuming. We would want to show that 3 does not divide x minus 1. That is, we would want to show that x minus 1 is not equal to 3j for any j in the integers. And how to do this would be pretty difficult. So we're assuming that x squared minus 1 is not equal to a multiple of 3. Where do you go from there? I think this would be challenging. So I would say, no, this is probably not the way we'd want to go. This is a statement of the form if P, then Q. And as we said earlier, if it's a statement of that form, then logically speaking, proof by contradiction would look essentially the same. So if we were doing contradiction, we would be assuming the negation of P implies Q. If we're assuming the negation of P implies Q, that's equivalent to assuming P and not Q. So then we would be saying, suppose that x is congruent to 1 mod 3 and x squared is not congruent to 1 mod 3. So actually, in this case, actually, this would end up being a little bit more like direct proof. We would assume this to be the case. We would assume that x was congruent to 1 mod 3, and I think we could go from there and show that x squared is congruent to 1 mod 3. So I think it would actually end up looking a bit like the direct proof will look. But it's just sort of couching the entire proof in something that's not necessary, couching the proof in contradiction. And In this case, I think direct will be much more straightforward. So let's try to do this as a direct proof. Okay, let's try this as a direct proof. So proof, suppose that x is congruent to 1 mod 3. Let's then unwrap this definition. Then 3 divides x minus 1. So then 3 divides x minus 1, and that implies that x minus 1 is equal to 3k for some integer k, so for some k in the integers, and therefore we know something about x now. X is equal to 3k plus 1, where k is an integer. It's not absolutely necessary. Okay, great. Now we're trying to show something about x squared. So let's consider x squared. X squared is then equal to 3k plus 1 squared, which is 3k plus 1 times 3k plus 1. We would get 9k squared plus 6k plus 1 when we simplify that out. And we're trying to show, so maybe again a scratch paper on the side, we want to show that x squared is congruent to 1 mod 3. That's equivalent to 3 divides x squared minus 1, and that would be true if x squared minus 1 is equal to 3, say j for some integer j, and that means x squared is equal to 3j plus 1 for some j in the integers. So that's what we're trying to show. Looks like we're partway there. So when we look at back in our original proof, 9k squared plus 6k plus 1, that is equal to 3 times 3k squared plus 2k plus a 1 outside of that factor. And so we can see that. X squared minus 1 is equal to 3 times 3k squared plus 2k, and therefore 3 does divide x squared minus 1, and so x squared is congruent to 1 mod 3. And then we've done a direct proof of that statement. So some general patterns to notice. If you're proving a statement of the form if P then Q, then theoretically any of those 3 techniques can be used. But if we would always want to look at the original statement P and say, okay, if we assume P, does that give us some mileage? Does that get us somewhere? If not, then we'd want to look at the statement not Q and see where does that get us. If not Q is a more useful statement than P, then we would either want to use proof by contrapositive or proof by contradiction. If assuming P gets us somewhere, then we can use direct proof. If we're trying to prove a statement that does not have the form if P then Q, then we could either use a direct proof or use proof by contradiction, but we cannot use proof by contrapositive if the proposition we're trying to prove does not initially have the form if P then Q.